So thanks so much for having me. I'm very, very sorry that I can't be in person. I really plan to be there.
Recording in progress.
But, you know, we live in turbulent times. It's my pleasure to talk to convey to you what I mean with network morphologies to store memories. And I would like to point out that I actually have two affiliations at the moment. I'm a professor at the Technische University of Munich and still in Göttingen at Max Planck. So I will take you on a journey to unveil how math can help us to understand life by first looking and marveling at what nature can do, and then using mathematical language to understand what's going on. And then taking it the next step further and telling you how looking into mathematical models can also inspire the next step to how to look at nature. And so the system I'm looking at is fluid-filled networks. So that can be the vascular network pervading your body, the venation network of leaves, or in a very pure form, the entire body plan of fungi and slime molds. Now, for the functioning of organisms, these networks and the proper morphology of the networks is crucial. And so now what life does is that these networks are dynamic. So an individual tube, if I zoom into such a network, actually adapts over time, shrinking or dilating its diameter to make sure that the morphology is proper and fulfilling its function. Now, how does it work? Like, you know, what governs these dynamics of this adaptation? And here it's inspiring to think that what combines all these different networks is that they have fluid flow pervading their tubes. And so flow can actually be information. Flow can exert the shear force on the tube wall. It comes with a hydrostatic pressure, or it can transport signaling molecules. And now in a setting where the tube's walls are live, and so they can respond to the information provided by the flow. And this can give rise to very emergent dynamics. So again, let's zoom into that single tube. So if, say, there's an increase in shear force, and due to this increase in shear force, this tube dilates. Now, this obviously changes the flow in the tube itself, but since we're looking at an incompressible fluid in a network of tubes, the flows throughout the networks also change. And that means that, you know, the shear force that's acting on a very distant tube is also changing. And you can see how a feedback between flows and network morphology emerges. And I want to understand exactly that feedback. And I want to study how the hierarchy, how the topology, how the adaptability, the responsiveness of tubes is contributing and governing this feedback. But today, as promised, I will take you on a journey of how math can help us understanding this feedback. And so this is a story about hierarchy. And so the tool that we're using is to not look at vascular networks in themselves because they are sadly hidden below our skin and hard to image and quantify. Instead, we're using Physarum polycephalum as a network-shaped giant cell. And here you see Physarum crawling on a petri dish where these black dots present food. And this happens on a time scale of 3 days in total. And so what you see here is that this organism behaves as a single giant cell with a mesmerizing shape of interlaced tubes as a network. And now this network is very, very dynamic and adapting continuously as the organism forages for food. If you zoom in, what's the organism is actually built of is a network of tubes that on the time scale of, say, an hour is very static network. But the tubes itself are very dynamic. You can see them here contracting and dilating over time rhythmically, here with a frequency of about once per minute. And this is driven due to an actin cortex contracting and thereby driving the liquid cytoplasm inside these tubes to flow forth and back. So we here really see fluid flows pervading these tubes. And the key is we can quantify it all. Now, having introduced this model system, and I should mention that it is indeed actually a single cell, but it has thousands and thousands of nuclei in itself. It's a gigantic syncytium. I want to take you on a journey to unravel the following mystery. I'm going to show you this movie one more time. Again, this is Physarum. These are food sources. I want you to focus on the location of the food sources while we play part of the movie again. You see that over time, the food sources are fully exhausted and consumed. Now the question is, can you still tell me where the previous food source in the center was? I believe you can. It was there, right? So how did you spot that? You spotted it because there's this pattern of thick tubes surrounding the former food source. And this observation ignited the idea that this pattern of where I have thick tubes and thin tubes is actually constitutes a memory over past events. And so the question is, how can such a network now encode the nutrient source location? And does this imprint of a food source really constitute memory? To answer these questions, we, namely my PhD student, Myrna Kramer, did the following set of experiments where we reduced the complexity of our experiments by making sure that we're looking at a network that is static over the course of our experiments. And so what we now do is that here at time 0, we present a food source and we follow the reorganization of the network as the organism reacts due to the food source. And here we're mapping out how tubes dilated or constricted over the course of the experiments, taking the difference between 45 minutes and 0 when the stimulus is being applied. What you see is that really within the first 15 minutes, there's a new hierarchy of thick and very small tubes being established in the network. A hierarchy that persists as the experiment goes on. So what sets up, and this is the hierarchy to the back, and very at the front, we see that tubes very close by actually strongly dilate, whereas at the back, tubes mainly shrink. So what is setting up this increase in hierarchy? To unravel that, we further quantify the data. And so what we do is we actually now measure the dynamics of all individual tube segments within this entire network as a function of the distance to the food source. So this is the distance of the segment, individual segment to the food source here. And now over time, you see the dynamics of the relative tube diameter. And so this is averaging out this fast scale contractions, just looking at the trend of how the diameter changes. And so we normalize that compared to before the stimulus, which hits at 0. And so what you see is that there is a wave of dilation propagating into this network, which goes hand in hand with tubes that are further back shrinking at the same time. This is in line with conservation of fluid volume. So if a part dilates, the other part needs to constrict to conserve volume. Now, what is the most important takeaway of this observation is that this the speed of this dilation has a velocity of 15 micrometers per second. And so this is exactly the velocity with which particles would be transported in the fluid flows that we observe in the tubes. And so now this observation of dilation and the speed of the dilation front sets up to a hypothesis. First, from the dilation, we hypothesized that what the food source does is actually that it triggers the softening of the tube walls, which are made of this actomyosin cortex. Second, due to the wave speed of dilation, we expect that the softening signal is actually spread with cytoplasmic flows. And now the key is that we can, we can cast this into a theoretical model, and the theoretical model can then make predictions that we can then use to look at our experimental data again. And so what we do to write down model equations is, first of all, to undergo one more step of simplification, which is to realize that in the end, this dilation is actually more or less a one-dimensional process from the food source into the network. And so we're going to describe it as the release of a softening agent of concentration C that is advected with the fluid flows along a tube. And now the physics of this process are fully defined. We have a one-dimensional numerical model describing the flows with Stokes flows, have a closed boundary condition, and we use physiological parameters throughout to set the parameters. And now this model makes predictions of the dynamics. And so here's one prediction. So what we measure is the dynamics of the tube diameter, first close to the tube stimulus, to the stimulus side, and in green further away. And so again, 0 is when the signal hits. And so you see that there's a tube segment close to the stimulus, dilates and then sort of stays as this dilated state, whereas a tube segment in green that is further away shrinks when the closed part start to dilate, and only later on, when the signaling, the softening molecule reaches that site, start to dilate as well. It also allows us to identify another observable that we can quantify our data with, namely response time, which we term the time between when the stimulus hit and the minimum at which a tube segment starts to dilate. And now we can use these predictions to go back and actually look with different eyes on our data. And so what we're going to do is actually now we're going to look at all the tube segments that we measured in our experiments and automatically quantify if their response follows the dynamics of the blue curve, namely dilation only, or of the green curve of first shrinking and then dilating. And indeed, for reference, you have the theoretical results at the bottom again, and at the top now you have the experimental results where we automatically quantify the dynamics of all tube segments, and you see that they indeed fall. This is showing the average of all blue and all green data respectively, that close to the stimulus tubes just dilate, and further away they shrink and then dilate. And again, also the response time scales as predicted from the theory with internal parameters of the model. So this allows us to now deduce that indeed this is what's going on, that we have a softening molecule that is triggered due to the response to a food source that is softening the tube walls and hence driving the dilation that is graded since the transport of softening molecules governs where the softening goes. And so now this brings us to the question, does this constitute memory? And so if you have memory, then it should be something that is also being read out and influences the response of the organism when it's facing another challenge. And so sadly, what we cannot do is take exactly the same specimen and have it go, put down the stimulus at a different location and see what it does, because it already responded to this food source. But actually going through those thought experiments, we see that, what happens in the progress of responding to food sources is that there's a pattern of thick tubes being established. And so if we actually look at the initial network, we see that from the previous past of the network, there is actually an existing hierarchy of thick tubes in the network. And so we can now see if this pattern of thick tubes is actually influencing the response to the new stimulus. And indeed, what you see is that these thick tubes here, they grow even further due to the food stimulus, whereas those at the far rear here, they don't. And it's very intrinsic to the system that indeed the existing hierarchy is here being read out in responding to the food stimulus, because the mechanism is the transport of a softening molecule, and the softening molecule will be transported by the flow along the routes of high capacity, namely the thick tubes. And so it takes the route along the thick tubes, so it reads out the previous information of, you know, where thick tubes have been stored, and therefore shows that indeed memory is being read out. So this concludes my journey to tell you that the hierarchy, so the patterning of thick and thin tubes within the network actually stores information about the history of events. And here you saw how casting our observations into a mathematical model really helped us to identify the mechanism that is controlling the process. But now I want to go one step further to show you the beauty of math, of how mathematical models can also really drive us to understand dynamics. And again, I will follow the idea of memory formation, but now in a theoretical context. And so I will ask the question, how can in general any flow networks encode memory despite the noise that we have in any biological system at the same time? So we're going to ask to, you know, write imprint the stimulus, put down noise, and try to read the output. And so basically what we here overcoming with the theoretical model is that we couldn't redo the same experiment with Physarum because the network kept changing as we were playing with it experimentally. But now in a theoretical model, we can actually do it, right? We can write different stimulus starting with the same initial condition and ask, you know, how does it impact the memory formation process? And so this is now work of my PhD student, Kamal Batakhaya. And here, to set the stage for the theoretical model, we're going to go back to a very simple description of flow networks that dates back to Murray in 1926, so almost a century ago. And so he successfully described flow networks as your vasculature as minimizing dissipation, which in mathematical terms is the flow rate squared over the capacity of a tube, constrained with a maximal building cost that is here written in a general form and can constitute for, say, gamma a half, then this is actually the volume of the tubes. So you have a certain amount of volume available, that's your building cost, and you want to distribute it such that you minimize dissipation. And this is a well-versed model that's been used in particularly over the last 20 years repeatedly. What is mathematically very beautiful is that, you know, given an initial network geometry, you can really solve this equation with a Lagrange multiplier. Which means that if you start with an initial setup of conductances and flow rates, which are determined by what's the pattern of inflow and outflow, you can then from these deduce what should be the ideal conductance of the tubes, individual tubes, if I want to minimize this dissipation. And so by applying this rule iteratively, I eventually will find actually a local minima that's minimizing dissipation at constant cost. And so therefore we here have a simple mathematical and well-established model that we can use to now probe, can we understand memory formation in general within this framework for adaptive networks. And so what we're going to do now is we're going to have a different setup from the boundary conditions wise. So here all nodes in the network serves as inflows, and the node in the center is an outflow. You can think of it as a leaf where this is a stem and these are the sites in the leaf of a plant, say. This is an initial random network with random conductances. And what we're going to do now is that we're going to apply an additional inflow at a select points of nodes in the network and minimize dissipation. And we see that a hierarchical network forms that is directly connecting these inflows to the outflow. And there's a distinct pattern. Now we're going to turn off this additional inflow and keep the network minimizing dissipation. Oh, well, that does not necessarily look like there's any memory of this location there by visible eye. But we can actually probe this now by applying, and again, stimuli at various locations around this network and see how the network responds. So this was writing the stimulus, and this is when the noise acted, and now we're going to read it out by putting down, moving the stimulus at different points after on this data set, and see what is the dissipation energy, minimal dissipation energy that I'm measuring depending on where I'm probing for any memory. And so this is what we see. So here we have a comparison of a trained network in red versus an untrained network. And along the x-axis, you see the angles of the stimulus angle at 0, at theta 1, and the probing angle. And so you see a distinct minimum in the energy of the system when I probe the network at exactly the location where I initially trained the network to be. So indeed, there is a memory of this network of the past stimulus. So how can that be? Well, to probe, we actually looked at the dynamics of the individual tubes and their conductances. And so what you see here is now plotting during the iteration of minimizing dissipation, the change in individual conductances over time versus their conductance in the first place. So these are the big tubes, these are the small tubes. And you see that dynamics actually fall into two categories. One, the large tubes, which more or less hover around, fluctuate around 1, so they grow and shrink a little bit. But then there's a sharp transition at a certain threshold where tubes that are smaller, they actually keep on shrinking, and they eventually vanish. And these dynamics are actually independent of the system parameters and persist also if I apply a load shown in gray. And so here's a visualization. So you see here color-coded the conductance and a logarithmic plot of the individual tubes. And you see that the low conductance ones, so the blue and green ones that still exist at a certain time, they actually vanish over the course of the simulation. So what we see here is that the memory is actually stored in the vanishing links. And now the beauty is that this we cannot only study numerically, and I should point out this was all done for gamma half, which was the constraint for where the building cost is the volume of the tubes. So what we can do here, and I will just briefly touch it, is that you can actually analytically solve the dynamics of these tube segments because this model is so simple. So you can really calculate what are the dynamics if I calculate the dynamics in a tree, and I know all the flows, and I look at under this minimization rule what would happen. And indeed, I find that the change in conductances falls into 3 behaviors, hovering around 1 for thick tubes and the thin tubes decaying with a power law of 1/3, as we observed numerically. And indeed, this behavior is totally consistent with our numerical simulations. I won't go in detail here, but just saying, like, we're doing the calculations on the tree, where it's all doable to do these analytical calculations, and they fully describe the dynamics in this circular geometry that we solved for numerically. The more important, so we understand that really indeed memory is where the thin tubes vanish, and this can be corroborated entirely with analytical results. But again, it shows you how also analytical results can go beyond, because we can do this calculation not only for gamma half, but obviously also for gamma being a parameter. And so if we do this, the cool thing is that you see for gamma being equal 1, this exponent here actually now vanishes. So, which means that for gamma equal 1, or actually gamma being bigger than 1, those thin tubes won't vanish. And indeed, this is, when we then go back to our numerical simulations, we see that if we again look at the conductances and the dynamics of them, then all of a sudden, all tubes are hovering around 1. There's no shrinking anymore. And if we then do our experiments of writing a memory, letting the network relax, and probing memory, there is no memory. Trained and untrained networks behave the same. So there's no memory in these networks. So what is different about these networks if gamma is equal 1 or bigger? So turns out if this exponent for the building cost is 1 or bigger, then the cost for building thick tubes is so high that to minimize this compared to the dissipative loss, that the network just won't have any hierarchy. This forms an entire loopy network where all tubes are more or less, there's not much difference in the tube hierarchy. So there is no hierarchy, and because there is no hierarchy, there's no memory. And so, this mathematical model showed us in the end that information is stored in vanishing tubes. And so the hierarchy of the network is the mean, the pattern of thick and thin tubes, to store information, but it's at the same time a prerequisite to do so. With that, I will just give a short overview of what we're interested in topology. Here we're looking at how it stabilizes flow patterns, how loops increase over flow, and also in adaptability, how the dynamics of individual tubes can increase, transport, flux, absorption of these networks, and even drive self-organization and optimization of networks. And at last, I'd like to make a pitch of why I believe that solving the physics of flow networks is an effort that's worth doing, and that intrinsically combines mathematical models and experimental observations at the same time. So, just to line out, this is us, this is humans, and we're filled with flow networks, starting from the vasculature, but also going through our bronchi, our whole intestinal system, and so on. We're filled with flow networks, and they're also key building block of applications as porous media, and for designing smart materials or synthetic organ printing. Understanding the dynamics of this self-organization is challenging physics, and combining math and experimental observation will solve it. With that, I would like to thank my group, funding, and particularly the 2 PhD students, Mona Karma and Kamal Bhattacharya, whose work I talked about today. Thank you.